Good afternoon, everyone. Welcome to the afternoon session. Please grab your seats. Okay, we've got a slumber slot now, but I know you're not going to fall asleep because EECA are actually up to some very interesting things. So Vince is here. I'd like to introduce Vince to talk about what the EECA Society is up to, various bits of analysis and research which is carrying on. So the floor is yours. All right.
So this question, what is EECA up to? It's the second most common question I get. The first one is who is EECA? So in case you're not aware, we're the Energy Efficiency and Conservation Authority. We're a government agency tasked with promoting energy efficiency and renewables. So when we get this question, it's sometimes it's a positive sense, sort of, or an inquisitive sense. Sometimes it's a little bit accusatory, like, what are you up to? But yeah, we try and be open. So I've got three messages. This is kind of the end, but it's good to put it up front sometimes. The first one, I'd sort of summarize this as don't forget about energy efficiency. And it happens all the time. So, and we keep saying it, kind of feel like that record, but it's kind of, we need to, because it does get forgotten. But we're getting there, I think. The next one, if we're going to electrify, we really need to be careful about peak demand. And there's been a lot of stuff on this today, and I think it'll carry on. But yeah, that's an area that we're looking at. And this last one, it's I think somebody else said it, sort of don't get stuck on the technology. Like, technology is part of it, but actually, in order to get the stuff to work, we need to get sort of the end-to-end system. So they need to try stuff out and give it a go, and then we might actually get the sort of the full system that we need. So we've recently refreshed our strategy, and I guess there's a lot of stuff on there, but I'm just going to talk about our purpose. The purpose is to mobilise New Zealanders to become world leaders in clean and clever energy use. And the key bit there is the clean and the clever. So it's not enough to be just clean. You've got to be clever while you're doing it. And that's, I guess that's where we come in, because energy efficiency is all about clever, but it also has a clean aspect as well, because it makes it a lot easier to be clean. So what does clean and clever look like? It looks like electrification, but only when electrification makes sense. So we don't want to electrify things that don't make sense. There's some examples of those, but I won't get into them today. Renewable generation, again, where it makes sense, where it's effective and cost effective and appropriate. Energy efficiency, that turns out we pretty much do that all the time, but only because most of it actually makes sense. But there is some energy efficiency you don't want to do, but not very much of it. And again, peak demand management. Again, we don't actually do enough of this, and we need to get better at it. So there's a couple of other things down the bottom there, which I'm not going to talk about, but people always kind of, I think they're sort of further down the road, but mode shifting, just excuse the pun. Mode shifting and demand reduction, but hopefully we'll get to those. So our approach, looking at network peaks, I guess traditionally we've always looked at energy efficiency in terms of kilowatt hours. And kilowatt hours can reduce network peaks, particularly if you take a broad-based reduction. If you take 10% out of the load, well, the peak's probably going to go down by 10% on average. And there's technologies in there that will do that. Lighting and space heating are good of those. And then this sort of second aspect of demand response, this is a kind of a new area for us because we haven't really played around previously with when should you use power. But as it turns out, if you want to have a high renewable grid and you want to have low carbon and you want to do it without massive infrastructure build, you kind of need to flatten the peaks out. So we're starting to look more closely at some of these demand response aspects. And obviously EV charging is a common one that we talk about, and hot water is another one. And I'm just not really talking about buildings today, but I just put this up because when we look at things you can do to make buildings more efficient, they're the same things as I put up on the previous slide. And so there's quite a lot of overlap there, but slightly different methodology. This is probably done through the building code and retrofits, but yeah, there's more than one way of looking at the problem. So let's talk about assumptions. Assumptions are really important if you're running a model, and you can't really get a model done without making assumptions, but sometimes we make assumptions that aren't true, and then we rely on those assumptions and carry on, and all of that stuff is wrong. I just thought I'd throw up a few that we come across. So the first one, peak demand is responsible for most of the CO2 emissions. Now, that's not true right now. Now, it may become true in 10 years' time when those big thermals are shut down and you're only using peak generators to meet peaks. But it's not true now. And so if we get too carried away with this as an assumption, we could go down the wrong road. The next one, and this comes from I think that the history that if you go back 20 years, all hot water systems were controlled and they weren't contributing to peak. This used to be true, but actually it's not true now. But so we're trying to dig into some of these assumptions and say, actually, have we got some evidence that says that they're not true? Have we got evidence for an alternate reality? The third one there, I mean, this actually tripped us up ourselves. We sort of started with this and said, actually, most New Zealand homes that people believe today switch off the heater over the peak. They just cool down too fast. Now, that is true for most New Zealand homes, but it's not true for all of them. And so for that 20 or 30 or 40% of homes, we don't need to heat them over the peak. Or maybe we don't need to heat them. So again, there's all of that space heating load that's going on with homes. Could it be demand response control? And then this last one's kind of interesting because it's a little bit true, but it's really not helpful. And that at the moment, if you increase overall load, maybe thermal does go up. It's not all going to be powered by coal, but again, that EV will be in the fleet for a long time. So it's got an element of truth, but it's really unhelpful for the whole EV story. So again, it's a sort of we don't want to allow some of these assumptions to flow through without being kind of tested or translated for the general public. So this sort of thing is what's driving a lot of our research work at the moment, because you can't challenge well-held assumptions without really good data. So in terms of energy efficiency gets overlooked. So we thought we'd give it its own story. And this is a report that we've done recently. And I guess the trick there was that we talked about energy efficiency a lot in the past, and we talked about how there's really good payback, and it's economically efficient, and it gives you co-benefits and all these other things. What we did in this report is we put it on a level footing with generation. So generation is generally costed in a sort of a levelized cost sense, so dollars per megawatt hour over the life of the generator. And so we did the same thing for some energy efficiency intervention. And so what we found is there's 7,000 gigawatt hours a year, that's the x-axis. And across these different categories, the blue ones are business, green ones are residential, that the cost, the levelized cost comes in around $10, $20, $30 a megawatt hour. Right, so that's, compare that to a wind farm, a good wind farm, maybe 70, a good geothermal, maybe 80, good grid scale solar, maybe 100. So a lot cheaper. So then we can put this on a graph and mix it up with the generators because we put it on the same footing. And so the black line there is a cost for a certain amount of gigawatt hour additions if you just use generation. And then if you use a mixture of energy efficiency and generation, you get the colored bars. So basically, we can start saying things like energy efficiency, it's like building new generation, only it's cheaper. And this has been really powerful for getting over that. Don't forget about energy efficiency. EV charging, we wanted to look at EV charging, and we found that there was a big gap in what we knew. We didn't know how many smart chargers there were. We didn't know how much they cost. So we did a bit of research, and key findings for us, we found a lot of stuff. But we found there's 65 chargers on the market, and 26 of them have smart features. And the smart ones cost about $500 to $1,000 more than the dumb ones. Now that doesn't seem like nothing, but actually in the context of something that's already $3,000 or $4,000, it's not that much. So that's quite hopeful for that. But what this research allows us to do is then take the next step, which is a cost-benefit analysis. It says the costs are on this side, and the benefits are on this side. maybe this is a good thing to do. So let's look out for that coming up. We took some pre-grid research and we took it a step further. This research, the data was all published, and we sort of looked at it and said, oh, this is a bit hard. So we got in touch with Michael and the team at Otago, who are very familiar with the data, and we said, hey, can you help us? And they did. That was great. And so what we can do is, from this, is not, we can't draw firm conclusions because it's a small data set, but we can start to challenge some of those assumptions about hot water. So that red bar there is the average hot water consumption at peak for that sample. Now that's not zero. Okay. Now this isn't conclusive. We're not saying that hot water consumption is X. We're saying it's more than zero. And that's really useful. It also helps to quantify the impact of lighting, because lighting is a really fun energy efficiency thing that you can do at low cost. Future work, so we're kind of just getting started on this demand response work stream, so there's a bit more to do. So we're going to do some work on hot water ripple control. There's a RFP coming up for that soon. We're doing a mixture of stuff sort of in-house and outsourced. So some of that's outsourced. The cost and benefit stuff, we're a long way through, so look out for a draft of that soon. Grid level benefits of flatter demand profiles. Again, we've got some modelling tools in-house that we can use, so we'll have a go at that, but we're keen to get feedback and engagement from people on whether what we're saying makes sense, because I guess there's no point in saying stuff that's not true, not accurate. But then we get into the really interesting stuff which we really need help with, which is the trials and pilots around trying stuff out. And as EECA, we can't really do that on our own. If we want to do a network trial, we need a network partner to work with. So that's really a key thing for us at the moment, trying to set some of those up. And some of those trials and pilots are around, are there standards and regulatory approaches that could be deployed to deal with it? And one of the things that EECA does is we manage a thing called the E3 program, which runs across New Zealand and Australia. It regulates appliance efficiency standards. And the South Australian government decided that they had a problem with demand, particularly demand peaks, and they wanted to regulate for what they call smart appliances. So every appliance in certain categories, which includes EV chargers, air conditioners, swimming pool pumps, and hot water cylinders, must have a demand response device that can be controlled nominally by a network company. Now, that went up for consultation recently. Some of you will have seen that, some of you submitted on it. That recently was actually approved by the Australian government. Now, the New Zealand government has to decide whether we go along with the Australians or we can split off. And we sometimes split off into something different. So it's quite an interesting space, because I think the regulation is it's useful, but it's not necessarily the best way of doing it. And I think that it's a little bit early in the whole space. So I think there's a much sort of deeper conversation we had around that. So when we put it all together, the research helps us deal with these assumptions. It gives us information about technology. It tells us about current use profiles, and it also tells us about what the customers need. And then we do analysis, so that's your cost-benefit analysis and models. And then when you've done all of those, you can start looking at policies and programs. And we have some questions that we have to ask. What's the problem? Is there a role for government? What are the options? And then we get into program design and trials. Now, sometimes we get these rather wrong way. We do the program design first, and then we do the trials. But ideally, we're doing trials and pilots first, and that will inform the program design. And so, yeah, restating key messages, don't forget about energy efficiency. EECA's now started working on peak demand, which we haven't done before. So we're going to play in this space. Hopefully, that's okay with all of you. But, if not, please tell us. Yeah, we think that to get the right answers, we really need to do more of this work. So, yeah, let's do that.